Now what is Z matrix? So Z matrix, as I said, it basically writes the internal coordinates of a molecule in a more tractable form. So let's say I'm taking the example of ethane. So ethane, I have carbon, I have another carbon, and I have CH3 here and the CH3 here. I'll just name them as 1, atom 2, atom 3, atom 4, 5, 6, 7, and 8. So to write the Z matrix, first I write my number 1 atom is carbon here, number 1 is carbon. Number 2 is also a carbon. So now number 2 atom is connected to number 1 atom. So 2 is connected to number 1 atom by a bond distance of 1.54 angstrom. This is an angstrom. Now what is my atom 3? My atom 3 is hydrogen, and that is connected to 1 by a bond distance of 1.0 angstrom. 3 is also making an angle with 3, 1, 2. So I write here 3, 1, 2, and the angle is 109.5. Number 4 atom is a hydrogen which is bonded to 2 by a distance of 1, and it makes an angle of 4 to 1 again. So I add angle 4 to 1 with the same angle of 109.5. Now your 4 also makes a dihedral. So my dihedral is 4, 2, 1, 3. So I can write 4, 2, 1, 3. So that's a dihedral, and that dihedral value is 180. Yeah, because this is a staggered conformation of ethane. So here you can see that 4, 2, 1, 3, which is 4, 2, 1, 3 forms a dihedral of 180 degree. Similarly, 5 is also a hydrogen connected to 1 by 1.0. It makes an angle of 512 of angle value 109.5. It forms a dihedral with 5124, 5124, and that angle is 60 degree. 6 forms, where is my 6? My 6 is here. So it is also a hydrogen atom, forms a bond with 2, bond distance 1. 6 forms an angle with 6 to 1, 6 to 1. Angle is again 109.5 degree. And 6 forms a dihedral with 6 to 1, 5. 6 to 1, 5 forms a dihedral of minus 60. I just erase that, minus 60. Number 7 is hydrogen, forming with 1, forming a bond with 1, and that value is 1.0, and the angle it makes with 7712, again 109.5. So now atom number 6 is also a hydrogen which forms a bond with 2 of 1.0. 6 forms the angle of 6 to 1 with a value of 109.5, and then it also forms a dihedral of 6 to 1 5. Yes, and that dihedral angle is minus 60. Atom number 7, which is a hydrogen, forms a bond with 1 of value 1.0. 712 forms an angle of 109.5, and 7124 or 7126, we are trying to cover all possible dihedral angles, and that is 180, so that the full structure of the molecule is defined. Number 8 is a hydrogen connected to 2 by a bond distance of 1.0. 8 to 1 is the angle of 109.5, and with 8 to where is my 8? 8 to 17 is my dihedral of 60 degree. Okay, so this is the Z matrix of ethane. So if I have Z matrix, then I can easily get the bond angle and the dihedral values quickly, instead of looking at the XYZ coordinates of each atom and calculate bond angle and dihedral to make my calculations faster. Okay, so far what we have seen is that we can have our initial coordinates from protein data bank, or we can, if there is no structure available, we can generate a crude structure from homology modeling if you're interested by a molecule, or you can make a simple model by drawing, by ChemDraw, for example, if your molecule is small, and then you choose the right force field parameters. So choosing the right force field parameters is important because the library, some scientists are interested in water soluble proteins, so their force field parameters would be different than a set of parameters which are made with the aim of covering the membrane proteins, for example. Since membrane proteins are less water soluble versus the other set of proteins which are cytosolic proteins, so the parameters developed in this window versus that window will differ. So if you choose force field parameters which were made for membrane proteins, and now you are picking up those parameter files for a cytosolic protein and run your simulation, your results will not be very good. So that's another conceptual understanding you should have when you want to generate the different microstates of your system of interest. So you got the initial coordinates, you chosen the right force field parameters, and then you now know the different tricks of the MD simulations, the technique by which you will generate different microstates, and by those tricks you made your simulation much more practical, in a sense that you are you given your protein or your liquid a bulk-like behavior, so that there is no surface effect. So surface effect you demote by periodic boundary condition, then you apply the minimum image convention to cut down the number of original interactions to the same half of n into n minus 1, and then you used another trick called cutoff, by which you further cut down the number of interactions to make your calculations faster. So you are ready to go to generate the new conformations or the new microstates. And so how do we do that? So now we'll talk about how we propagate our system. How do we generate new microstate starting from a given microstate? So my given microstate is basically the initial coordinates which basically put up together, which will give you an initial structure.